Hello, my name is Glenville Pecor, and I'm basically going to be describing Newton's third law. First, before we have to learn Newton's third law, we have to learn, what does a force mean? Well, basically before we know Newton's third law, we have to know what a force is and how to add forces. So let's learn what a force is. Ignore the graphs right here; they're just a nice background because I will be going into those later. So don't these do not matter right now. Basically, the force is a push or pull upon an object because of the resulting from the object's interaction with an object. So whenever there is an interaction between two objects, there is a force upon each of the objects. When their interaction ceases, basically stops, the two objects no longer experience a force. Forces only exist as a result of interaction. So that's saying if you touch a wall, there is a force from your finger touching the wall. There's a force from your finger pushing against the wall. And since a force is their interaction between two objects, that means their wall has to have a force pushing against your finger. Now you're probably wondering yourself, how was what I said just true? Well, taken from graphs, this graph is from a different website because I don't own force plates, and force plates for me is the best way to show how Newton's third law is proved. And since I don't have any data on the force plates, so I got two graphs online. Basically, this put on Logger Pro. So basically, what this is a force plate. Uh, so basically, the red is force 1 in newtons. I'll explain what Newton is right after this. And the blue line is force 2. So basically, imagine you have two people standing right next to each other with force plates. You tell student 1 to hold their ground, force 1. You hold force 2 to say, hit force 1 as hard as you can. So when they do that, here's the part where they're not hitting. So after 20 milliseconds of not being hit, just a give or take, they hit each other. And if you look at these graphs, they're almost perfectly identical. The only opposite thing is that they're flipped. So you can say that, oh, force 2 is pushing force 1 to be like that. Force 1 has to be pushing like that. So there's a really good experiment to prove Newton's third law. Now, back to the basics. What is a Newton? Well, it is it's a type of force. A Newton is... Sorry, I meant to say Newton. A Newton is equal to the force that would give a mass 1 kilogram of acceleration per 1 meter per second. Now, how do I prove this? Well, a really good experiment that you could be done is you get, basically you have a scale that reads how many newtons you have and how to show that they work together, how newtons and the weight of an object work together. Basically, we're just going into how what I just said, what a newton is true. So you weigh on a Newton scale. You weigh weights. So basically, you get a graph with a y equals mx plus b, as in, because the y-axis is weight, and the x-axis is mass. So basically, weight is in newtons. Remember that. Weight's in newtons. So you weigh the object. You get the newton. You plug in into the graph. Oh, how much mass do I have? Let's say I have the mass is 1 kilogram mass you weigh on a scale. Pretend the scale is capable of holding this in this problem. So I do that. Plug in, and it would read. If it was 1 kilogram, it would read 10 newtons. I keep on doing this. So if I put like a 2 kilogram thing on, it would read 20 kilograms. So I plug it in, and it says about. And if I figure out that y equals mx plus b, so that means weight, which is y, which equals the slope, which give or take 10 newtons over kilograms, because it's the slope. You rise in newtons and run in kilograms, times the mass, because that is x. And in the equation, since they weren't perfect, you had an extra 0.002 newtons left over. That just means your thing wasn't perfect, but that's okay. because you know the 0.002 newtons are not should not be there. So the equation you get from it is weight equals 10 newtons over kilograms. So when you have a weight of 1 kilogram, that shows that it has to equal 10 newtons over a kilogram times the mass. So basically, sorry, not the weight. If the mass is 10, you plug into the equation. Oh, what's 10 newtons over kilogram times mass equal? It equals to the weight. So that is meaning of the graph. Now, with that in mind, that implies weight is also equal to mass times gravity, because gravity is weight. So that also implies that. So basically, you could get from this equation, since the units are newtons equals kilograms times, you can get also, because gravity is an acceleration down in meters per second, and mass is in kilograms, so, and weight is in newtons. So, basically, this proves that newtons equals kilograms times meters per second squared. And now let's make that nicer, because you're going to use using this in a lot. Newtons over kilograms equals meters per second squared. So that is how that all correlates with each other. Now let's go back to this graph. I want to say something that most people, before taking physics, would think is true. If you had a ballerina, a 12-year-old ballerina pushed against a 12-year-old ballerina that weighs about maybe 20 kilograms, and you have a 100-kilogram sumo wrestler pushing against the sumo wrestle. If you ask this to a person who's not taking physics, they would say, if you ask a question, who is exempting more force on each other? Well, what would the answer be? Well, most people would say, oh, the sumo wrestler, because look how big he is. That is wrong. If you look at this equation, we had a big muscular guy hit a tiny skinny guy with the force plates, and you got this. So with this, that shows that what most people think is true, if a sumo wrestler can push more force on a ballerina. Well, that's wrong. They both push an equal amount of force on each other. That is one thing I just want to get out of the way quickly. Now let's go to a real life situation. Now here's a good real life example. Pretend, see this ugly looking bus. Here's the bus, and that black thing is a bug splattered across the windshield. Basically what happened is you're on a bus and you're going on the highway. I don't know, so you're going on the highway at 100 miles per hour. 20 meters per second. And a bug flies and goes splat right into your window. Which, would the bus have more force? Or would the firefly have more force? Well, let's remember what we said about the ballerina and then the sumo wrestler. With that keeping in mind, the answer has to be, it's a trick question. They're both equal. Why are they both equal? Because if you go back to Newton's third law, for every action, there's an equal reaction. The fact that firefly splatters only means that it has a smaller mass. It can't withstand the large mass and the acceleration resulting because of the interaction. So that's how you use something in real life with Newton's third law. And how interesting is that? Now, basically, that is the whole thing of Newton's third law. Let's go to the summary of it. I'll put it in my turn it in folder on Google Docs, but this is just an example. I'm going to show you a summary, Newton's third law. Basically, third law says for every action, force, there's an equal opposite reaction. For forces are found in pairs. Think about a time you sit in the chair. Here's another good example. I'm going to say more examples to help, more examples I say, the more it will be, basically drilled in your mind. And we want that because these are most important things you could learn in life. So let's go back to the thing I was saying. Think about the time you sit in a chair, like you probably are right now. Your body exerts a force downward, and the chair needs to exert an equal force upwards, or the chair will collapse. It's basically an issue of symmetry. Acting forces counter other forces in the opposite direction. There's also an example of shooting a cannonball. Another good example. And this is fun, because who doesn't like shooting cannonballs? When a cannonball is fired through the air by the explosion, the cannon is pushed backwards. So you can also say, like shooting a gun, it's more common. The force pushing the ball back, the recoil, I was equal to the force pushing the can back. But the effect on the cannon is less noticeable because it has such a larger mass. Let's go back to the bus. When the bus is moving and the bug hits it, it doesn't really. The pushback is so small because the bus's mass is so much greater. It's like Jack and the Beanstalk, the giant versus Jack. That's how big they are to each other. That's how Jack's the bus and no, sorry, Giant's the bus and Jack's the little bug, or in this case, the cannon. Sorry, the cannonball. The examples are so basically that is what third law says. And I hope you learned everything in third laws here. And hope you have a nice day.